Hello, I'm Susan Nash with AAPG, and I'm delighted to have the opportunity to speak today with Gil Machado, who is with Chrono Surveys. And Gil, would you tell us a little bit about yourself?
Sure. Thank you very much, Susan. So I'm a geologist by background, and I did my PhD on stratigraphy, specifically biostratigraphy and petroleum geology. And I've been working in the industry for the past 10 years or so as an explorationist and also as a biostratigrapher. And recently I've started a consulting company, Chrono Surveys, and we've been doing in addition to normal consulting work, also a bit of research and development. And this today, Salt Biostratigraphy is one of those projects which is now matured, and we're now presenting
I'm
it.
really fascinated by that. And I know that a lot of people who are working in various areas, regions with salt will be fascinated by this. And so I'd love for you to talk to us about salt biostratigraphy.
Yes, absolutely. And thank you for the opportunity to talk about this. Indeed, I think one of the challenges now is to make the community aware that this is possible, that we can extract reliable and relevant data from evaporite deposits, which I think people don't really realize. So thank you for the opportunity to talk about this. So maybe I can go through the presentation and I'll present briefly what we've done.
Great, that's wonderful.
So it all started with the question if fossils can be preserved in evaporites, so in halides, anhydrite, gypsum, and other evaporitic sediments, and also in the sediments that occur interbedded with these sediments, so any salty shales and other sediments that usually are interbedded with evaporites. And the answer to that is that yes, they can. They can be preserved, and what we've done is to explore how we could extract those fossils from evaporitic sediments, and that was the main issue, I think. So this started with some some mine samples, and I'll show you some of the case studies that we've worked with. And what we've seen is that in mines, usually the halite, if it's not pure halite, so very white, pure halides, the geologists at the mine call it impurities of that halite contains. And that's exactly what we're looking for. These impurities, most of them will be just silts and clays, but some of them will also be microfossils, notably organic microfossils. So in this cartoonish kind of reconstruction of an evaporitic environment, and this is from the current day Dead Sea. There's a riverine input and also blown in by winds. You have clays and silts, but you also have spores and pollen of any vegetation that is surrounding the evaporitic lake or sea. If it's connected to the sea, so with normal marine conditions, and if you have periodic invasion of seawater, then you can also have algae and whatever living creatures exist in seawater coming into to these evaporitic basins. So all of these have the potential to be preserved. We just needed to find a way to extract these fossils which were preserved from evaporites. And it's not straightforward, and this may justify the lack of studies throughout the last decades regarding evaporitic sediments. So there's a few descriptions of the methods and interesting results from evaporites, but I could only find a few dozens, if that much, compared to maybe thousands of publications regarding biostratigraphy of all ages. So there's really very, very little published work on salt biostratigraphy. If you narrow that down to salt biostratigraphy applied to the petroleum industry, then it's even less. I think I could find only something like less than 10 publications regarding salt biostratigraphy applied to the petroleum industry. So we were trying this at the lab, we tried several techniques. The normal techniques to extract polynomers, so polynology techniques, usually use acids basically to remove the mineral content of sedimentary rocks. That doesn't work with evaporites, so you need an adapted method to basically dissolve away the evaporitic minerals, be it halite, anhydrite, or gypsum, or whatever it's present, and to isolate the organic content. So it requires an adapted method, and this may justify why it hasn't been used so much. So basically, the recovery of these microfossils will depend on the original fossil contents. Of course, if they don't have fossils originally, I don't work miracles, so I cannot extract them. But if they are present, then it's only a matter of the preparation method, the way you prepare the samples. If you know what you're doing and have some information on the mineralogy of your samples, then you can adapt the methods to be able to separate the organic content and the mineral content. Once that's done, you just mount the organic content on a slide, and you can observe it under the microscope the same way you do with normal polynology samples. So it's not that complicated. It's also good because the amount of sample that is required is not that much. It's a bit more than normal sediments. So for example, if you have shale, you may only need a few grams of sample. If you're working with evaporites, you'll need a bit more, so around 100 grams, depending on these impurities, the contents, or the amount of these impurities in the evaporite sample. So
it's exciting that you can use cuttings.
Yes, well, it can be a challenge, especially depending on the drill bit which is used. So they can be basically washed away when the mud logger is analyzing the samples. But if there's something left, then if there's enough sample, then it's good enough to work with. It's possible to work with cuttings. That's a very good use. So you can work with of course with outcrop samples, core samples, and also with cuttings. And I'll show you some examples of what we've done. So we spent the last year or so refining this technique, and initially it wasn't really working because we didn't really know how to tackle the samples, because it was so different from everything else that we were used to process. But now we've refined the method and we have something like 90% success rate, and that's pretty much the same success rate you have with normal samples, so non-evaporitic samples. So we're quite excited with the potential use of this technique. So I can show you some examples where this started and what we've done.
That would be great.
This is a salt mine in southern Portugal. It's an underground mine. They mine it for salt. Most of the salt looks like this dirty halite that we see here, which has these pinkish, bluish, and grayish hues. And those are exactly the impurities we were looking for. In addition to that, there are some interbedded sediments. So this dolomitic siltstone, some cherty gypsum, and organic rich shale. And then you go back to dirty halite again. So all of these were sampled. We got organic particles from all of them. The only one which was a bit more difficult to get anything relevant out of was this dolomitic siltstone. And this is probably because it's been either during deposition or during diagenesis, it was exposed to oxidative conditions. And that's a killer for organic matter in general. So we could only find some oxidized and degraded organic particles that were not very relevant for biostratigraphy, but all the other samples we were able to extract spores and pollen, and also phytoclasts, meaning little plant remains, and that's basically another name for vitrinite. So that was an add-on discovery, I would say, from this method, that not only can extract spores and pollen, and I'll show you also some marine polynomers, but you can also measure vitrinite reflectance, and with that to obtain quantitative.
That's amazing. That's a huge
maturity.
plus.
Yes,
Yeah.
that's a huge plus. I think I think some companies won't be so much interested in the biostratigraphy, but actually the being able to measure the thermal maturity of the salt sequence is actually a big plus.
That's huge.
Very important piece of information, I would say, in many basins around the world. So that was one of the first finds. These were probably the toughest samples that we processed because they are so varied and the mineralogies were so different, but we managed to extract organic particles from all of them.
Great.
I initially presented these results in one of the AEPG's workshops in Europe. This was last year in Poland, that focused precisely on evaporites. During that workshop, there was a field trip or a mine trip to the Wieliczka salt mine, which is known for, it's actually not an active mine for the ore, but it's now active only for touristic purposes. We were lucky enough to go around with a few Polish geologists that knew the mine quite well, so not just the touristic tour. And I was able to sample also different types of evaporites and also these interbedded shales that occur. So the lithologies here are quite varied, several types of salt and also the types of shales, and there's active tectonics during the deposition, so it's actually quite a complex geology. So we sampled all the different types of lithologies, and in this case, all of the samples were productive. And we were able to find the pollen and spores, as we did before, and also some dinoflagellates, especially on the shale samples. So that means that this was under marine influence. You had episodic inflow of seawater, and you had these dinoflagellates, which are very useful for biostratigraphy, even more than pollen and spores. And again, we found these phytoclasts, aka vitrinite, which again can allow to determine vitrinite reflectance, and with that, the thermal maturity of these rocks. This was also quite, for us, quite exciting because this was a completely different geological setting. This is a Miocene salt, so quite different from the early Jurassic salt that we had examined before. So we're, showing that the technique is applicable to different types of settings, different ages. I'll just show one more example. This is from a salt mine. Samples were provided by a Moroccan colleague, which we are acknowledged to. And in this case, the age is quite similar to the one in Portugal, so it's early Jurassic. In this case, it's not mobile salt, so it's not a diapir. It's interbedded with also several types of shales. And also here the lithotypes varied quite a lot from these shales, which were not that different from normal shales that you would analyze for palynology. But then pinkish halides, more brown and black.
Does that indicate a reducing environment? Does the pink indicate a reducing environment?
Well, actually, usually the opposite. At least with non-evaporitic samples, we usually run away from these pinkish and reddish colors, which usually mean oxidative environments.
Oh, okay.
So we decided to.
Iron. The presence of iron, but that would make sense because that would be iron oxide instead of iron.
Yes, exactly. Yeah. So that usually that red color is oxidized, the oxidized version of iron.
Right. Yeah.
So we were a bit weary about these samples, but we decided to test them, and voila, they also provided spores and pollen and phytoclasts. So the quality was not as good as the other types of samples, where these more brownish and blackish samples, but they were also productive. So again, we were quite excited that even these lithotypes that we didn't really expect to have much results from, they're also productive. We can also extract polynomorphs from these types of samples. So again, different environments, different types of lithologies, but they were all productive in different proportions. Some of them were quite good, others not that good. But that's also what you find with normal non-evaporitic samples.
Nice.
So so we're quite excited with this. It is from the point that we managed to master the technique to process these samples, then the results have been very, very positive.
Well, I'm so excited about this, and glad that you'll be able to go into more detail when you're doing, I guess, lunch and learns for the European region, and also a course. So this will be fantastic.
Yes.
I think it's so valuable.
Yes, absolutely. So just to add that since this, we've tested 2 or 3 more sites, outcrops, and also mine samples that were also productive. So we tested one of the Zechstein salt from northern Poland, and we also analyzed some gypsum samples from an outcropping diapir from Portugal. And again, we had positive results in most of the samples. So we've shown that it's possible to work with samples from Permian to Miocene age, different types of settings, different types of lithotypes. So it does seem to work quite well. So we're now, I think that, as I was saying, I think the main challenge, and I thank AEPG to give me the opportunity to do this, is just to make people aware that this is possible. This can provide very valuable results in facies that usually it's just a hazard to drill through, but you can actually get relevant information from these type of samples.
Oh, it's just amazing. And I'm thinking of all kinds of applications, not just in the, say, the Gulf Coast or some of the obvious places or in subsalt, but also in areas that are onshore where you have to drill through evaporites. I was thinking some Permian and some. It's so great.
Yes, no, absolutely. If you look at the map of salt basins around the world, I think there's only a few of them which are not petroleum provinces. So that salt, as you know, is a major element of petroleum systems, and it's you know, as a seal, as a thermal conductor, so it plays such an important role. And I get the feeling that we don't know much about it in most of the basins. We have a rough idea of the age because we can date the rocks below it and above it, but we usually don't have any idea on the thermal maturity of the salts, and we have no idea of the ages.
Oh, I totally agree. We usually just look at salt diapirs and think, okay, this is structural influence, but not at all into the salt itself.
Absolutely, yeah.
Well,
so yeah.
This is great. Well, I want to thank you again. And again, this is AEPG Science and Technology Showcase, and our guest has been Gil Machado, and we're happy that he will be presenting more in future events. So thank you.
Thank you very much. Thank you for the opportunity. And thank you, Susan.
Thank you.